So today we're going to be discussing binary tree. So like linked list, binary tree is also a linked list. It's actually a abstract. It's a data structure, and the basis of this data structure, like linked list, is also just an array. So as we remember in our linked list, it was an array of nodes, and the nodes that we create are based on this record data type that we have created, like here, this way. Okay, and afterwards, when we have created this node, we actually basically connect them using these algorithms. And if you add a node, you can add it anywhere in between your array, as opposed to how your conventional arrays work. Your linked list operates this way, that you can add a node anywhere in your array. It could be at the end, at the start, in the middle, wherever it is. And basically it has two data items. One is the actual string value, which is the value that we're talking about, and one is the pointer value, which points towards the next node that's coming after. So basically this pointer is telling you which node comes after this node, and this way you're controlling the entire flow of your linked list. Similarly, what we have here is a tree. Now the major difference between linked list and your binary tree is that your binary tree has, just like linked list, it has nodes. But the thing is, apart from just having one pointer in your linked list, your binary tree has 2 pointers. Okay. Now those 2 pointers are pointing towards the left and the right. So for example, if I have this node right here, this node will also have, this has the data value. As you can see, it has C in it. And apart from this, it will have 2 pointers. Those 2 pointers will tell you that what node is connected to the left of this node and what node is connected to the right of this node. So if there are no nodes connected in either position, like we can see in this node right here, then those both pointers will be null. As always, when a node is not pointing towards anything, it has null as a pointer value, if we remember this. Okay. But that's basically the overall structure. But what we need to understand is how a binary tree works. Okay. Now imagine that we have this existing structure. This is what a binary, this is the logical diagram of a binary tree. So we have this root node, like we had the start pointer that's telling you the first node of your linked list. The root node is the first node that has been added to the binary tree. So this is only it's considered the root node because it was the first node ever created. It doesn't matter what value it has, but what matters is that it was the first node that was created. Every other node has to be attached on the left or the right of this node. Every node. Okay. So basically what we have is, this is the root node, and every other node is attached to this root node. Okay. Now, as you can see here, I have this structure right here. And if you look closely, it looks like this whole binary tree has 2 subtrees on the left and the right of this root node. And that's exactly what it is. This is a root node for this subtree. This is a root node for this subtree. And there are nodes that have no nodes connected to them on both sides, like this one right here. This is known as a leaf node. So this is also a leaf node. And that does not mean that they cannot have any nodes attached to them ever. They can, but right now they don't. So this is the current situation of our binary tree. It has these 6 values, 6 different nodes connected in this way. So now let's see how it works. How are these nodes organized? Now imagine that I want to add the root node with a value D. So now again, as we were allowed to add data values, we were allowed to organize our linked list based on the values stored inside the nodes. We are allowed to do the exact same thing here as well. It doesn't matter what order, chronological order that node had when we were entering into the binary tree. It could have been the last node, it could be the first node. It doesn't matter. but we are allowed to implement some sort of order with respect to where that node as is to be attaching in our binary tree. Now let's take, for example, I am trying to add the node D, now the value D. So this is how I will start taking my decisions on where that node is to be attached. So obviously, if I have a node, I just added a new value to it. That value is D. As we did with the linked list, we referred to the start pointer telling us which node comes first. And based on the value of the first node, we will decide whether we will store it before the first node, after the first node, in between somewhere, or at the end somewhere. But we need a place to start. And basically, in the linked list, the start pointer tells us that. The root node pointer does the exact same thing. It tells us where your binary tree starts. So technically, I will be referring to a variable just like the start pointer, but it will be called something like the root node pointer or root pointer, which will tell me which node is the first node. So if I have referred to the root node, I will end up with this node. Now, as you can see, I want to add the node with the value D in it. The principle states that I, first of all, refer to the root node. What is the value stored here? The value stored here is F. Now, D is lesser than F in our alphabetical order. So D comes before F, in which case, if it is lesser than, if it comes before F, if the value is lesser than this value, I will move to the left. If it is greater, then I will move to the right. That's how it happens. Now, this is the rule that I'm going to follow. So since D is lesser than F in my alphabetical order, and if you don't want to consider alphabetical order, consider the ASCII value. The ASCII value of D is lesser than F, in which case I will move towards the left. As you can see here, this C is sitting at the left of this F node. Now, this will be considered my root node right now, because right now I'm focusing on this. What is the value in C right now? It's C. So C, I'm comparing it to D. So since D is greater than C, as D was lesser than F, I've moved to the left. Now, when I compare D with this node, which is C, is greater than C, I will move to the right. So in which case, from C, I move to the right, like so. After this, since I'm here, after this, now look at this node. I'm at this position right here. I compare my newly added node, which is D, with the value of that's currently stored on this node. That's E. So now since E comes after D and D is lesser than my current value in my node, so that means I will move to the left of this node. So I will keep on doing this left and right transition until there is no more nodes either on the left or the right of the recently observed nodes. In this case, I will be stopping here because there are no nodes connected on either on the left or the right. But since I have room on the left and I have to move to the left because D is lesser than E. So that means my D will be associated it will be attached on the left of E. So as you see here, my D is attached on the left of E. So just a quick recap. I want to add a new value D. I will start at my root pointer and compare the value of my newly added node with the value of this. If the newly added value is lesser than this, I move to the left. Compare it to this. If it's lesser than this, move to the left. If it's greater than this, move to the right. Then compare it to this. If it's lesser than this, move to the left. If it's greater than this, move to the right. Now I will continue to do this until there are no more nodes to traverse, in which case the E will be the last node to compare. And since after reading E, I move to the left, why move to the left? Because D is lesser than E. I will move to the left, because of which my D node, my newly added node, the D value will be attached on the left of E. And this is how my binary trees addition of nodes works. If it's lesser, move to the left. If it's greater, move to the right. Now let's see if I want to add a new node, another node. In this case, I'm going to add the node with the value J. So I'm trying to add the value J. Now consider this. Of course, we will always have to start with the very beginning, the root node. J is greater than F, move to the right. J is lesser than S, move to the left. J is lesser than R, move to the left. And this is where I stop because there is no more values beyond R. So this is where J comes in, like so. As we saw a two-dimensional structure for our linked list for storing the information for each of the nodes, like so, there is a similar structure. As you can see, this is what it looks like, a two-dimensional array for storing the information regarding all of the nodes in my linked list. We have data values and the pointers and each index position for each node, so on and so forth. Apart from that, we have two variables that signify the start of my linked list and a free list pointer pointing towards the start of my free list. So next available node. If we remember, an empty linked list looks something like this. The start pointer points towards nothing. That's why start pointer has null in it. And free list pointer is pointing towards node number 1, which is the next available node to be used when data is to be added. Similar that type of data organization, similar type of data structure will be used for your binary tree. Now, this is what an empty tree looks like when I make it into a two-dimensional array. Now, each of these rows, each row signifies one node. This is one node. So as you remember in the linked list, each row signified one node, and each node is a record data type that has two values, a data and a pointer. Similarly, a binary tree has a similar type of organization, but the difference is that this node has three values. So when we're going to be creating a record data type for this node used in a binary tree, we will be using three data values X as opposed to the two data values in our linked list. Of course, we will need to mention pointers for both the right and left. As opposed to just one pointer, we have to have two pointers for each node in our binary tree. Now see this. This is basically an array. This is just an array. As always, all of these data structures are the underlying structure of these data structures is just an array. It's the algorithm that allows us to add these features of moving left and right and adding values in between. That's the algorithm, but underlying their basic structure is just an array. So like that, this is an array. This is an array. Basically this table represents an array of 7 nodes. There are 7 nodes here, and this is the index position for all of these nodes. Now, as you can see, this is an empty tree. There are no used nodes here. So one thing to note here is that instead of having something known as a start pointer that we used on a linked list, we have what is known as a root pointers. Now, since there is no nodes right now currently in my binary tree, you can see that the root pointer has null in it. And since the first available node to me for when I'm going to be storing data in my binary tree is the first node, so that means the free pointer is telling me which node will I be using when I want to add a data. And this is telling me that node number 1 is available for you whenever you think about adding data. Just like exact same working as we used in our linked list. Okay, now here is the interesting thing. This is one node. And if you remember that in linked list, we had empty nodes connected to each. So basically, if you remember here, even the empty list like so is connected to every other empty nodes. This is my first empty node is connected to the second node because it's pointing towards the second node. Second is pointing towards the third. Third is pointing towards the fourth. Fourth is pointing towards the fifth, so on and so forth. Similarly, our binary tree, empty tree, is also connected in a similar manner, but not towards the right, but towards the left. That's just the way it's designed. All of the empty nodes in a binary tree are connected through their left pointers. So as you can see here, the first node is connected towards the second node through its left pointer only. The second node is pointing towards this third node as it's connected as in the left position. Why do I know it's the left position? Because it's pointing in the left pointer to position. So the third node is connected in left position with the fourth. The fourth is connected in left position with fifth. Fifth is connected with sixth. Sixth is connected with seventh. Seventh is connected with nothing because it's the last node. But all of these nodes are connected together through their left pointers only. And the right pointers are currently empty. There's nothing in it. When the time comes of storing this binary tree into its appropriate position in our overall structure, then we will decide where this node has to go. And then, and according to its position there, we will decide if there's connected anything on the left or the right. But right now, this is, since it's an empty tree, there's nothing here. So this is our empty tree. This is what it looks like. And when we'll be creating an algorithm for designing an empty tree, we have to keep this overall structure in mind. Okay, now this is my partially filled tree. Partially filled. Now check this out. Imagine that this tree that we just added D with, this is represented like so in this two-dimensional two-dimensional array, or in a table form. Now, as you can see here, my current node, my root pointer is pointing towards node number 1 as the first node that's being used. That's true. This is my root pointer. And as you can see here, in this data structure, in this table, it states that node number 1 in my array index position, where the node stored on index position 1 has a value F in it. And what's connected on the left of F? The node containing C, the node containing, and on the right of this node is the node containing S. Now let's see, what node has C in it? This is the second node. And what value node has S in it? This is my fourth node right here. Just check this out. This is S, this is my fourth node. So that means my first node, which has data value F in it, is connected. The nodes that connected on the left is node number 2 with the value C, and the one that's connected on the right is node number 4 with the value S, like so. Similarly, when we come towards node number 2 with the value C, you see that node number 2 with the value C has a node with the value B on the left and a node with the value E on the right. So is there a node with value B in it? Yes, there is. That's the node with index position 3. So similarly, node number 2 with value C has a node number 3, index position 3, connected towards the left. 3 has B in it. And this node with the value C has a node with the value E on the right of it. And that is actually node number 6. So that's why it's pointing towards 6 on the right side. Likewise, you see that there is this node here. This is, as mentioned before, this is a leaf node. Why is this a leaf node? Because it has no nodes connected to the left or the right. It's the final node. So node with value B is actually index position 3. So what's on the left of it? Nothing. There's null. And what's on the right of it? Again, nothing. It's not pointing towards anything on the left or right. Similarly, you see that I have this node over here, E. Now, after E, there is nothing connected on the right of E. So similarly, node number 6 with the value E has nothing connected on the right of it. But what's connected on the left of it? A node with the value D in it. What node has value D in it? The node with the index position 7, like so. So E, towards the left of E, is a node 7 with the value D. So towards the left of E is D, pointed out by node number 7. And what's on the right? Nothing. That's why there is null stored on the right point. Same thing goes with the node S. There is nothing on the right of S, but on the left of S, there is a node with the value R, which is node number 4. There you go. Node R is node number 5. So that's why on the left of S is pointing towards node number 5 with the value R in it. And finally, the node number 5 with the value R is a leaf node. So that means it's not pointing towards anything. So that's why there are null values on the left or right of it. So this is basically what, okay, finally, what is the state of these two variables here? So obviously the root pointer is telling me that my binary tree starts with this node, and once I reach this node, I can start accessing all values from here. So I reach node number one, and this will automatically lead me towards all other nodes. By the way, that is known as tree traversal. We'll be discussing that a little bit later. That's a little tricky concept. Okay, and the free pointer is pointing towards null. Why? Because there are no more free nodes. We had 7 nodes in this array, and each and every node has been used. So there are no more free nodes available in this. So that's my free pointer is saying that there are no more available nodes, and that has null in it. So now let's check out the basic algorithm of different features provided in our binary tree. So as we discussed the algorithm in detail for your linked list, we'll be doing the exact same thing for your binary tree. So as we did with the linked list, we will also, okay, I've also mentioned the Python code side by side with every algorithm code that we studied. So it's going to be a good idea to look at both. I'll be going through the Python code later on, but right now we're going to focus on the basic flow algorithm so that we basically understand what's going on. Implementation into a code, that's not that much of a problem as much of understanding this algorithm first. So as we start off with adding an empty binary tree, as we did with an empty linked list before, we're going to do the exact same process here with an empty binary tree. Okay, so first of all, I need, as we did before, I need to assign a constant for my null pointer. Since my array is designed in my tree array, as the underlying foundation is just an array, it relies on index position 1 to 7. So that means I am using index position 1, and that's why, and index position 0 is not part of my array. In that case, my null pointer can be 0. If I were using index position 0 onwards, then my null pointer would have been -1. And as you can see here, the Python version 1, I'm using null as -1 because all programming languages mostly rely on the 0 index position. So that's why I will be using the 0 position as the first position. So, and my null will end up being -1. So that's not a big deal. In this algorithm, we're using null as 0 because we're starting index position 1 onwards. Okay, so having said that, now the time comes for me creating a data type, a user-defined data type, a record data type that is capable of solving my problem of storing 3 different values, 3 different types of values, namely 2 pointers and 1 data value. So as you can see here, I just created a 3 node data type that is capable of holding 3 values. So one is of the actual data, which is going to be the letter here. And the letter is going to be of type string. Similarly, I have a left pointer of type integer, a right pointer of type integer. As linked list, we just had 1 pointer of type integer. Now, since binary tree requires 2 pointers, we'll be adding 2 pointers over here. And this is all I need for my node, my record type in my node, and I can just simply close my record type over here. And now after this line, I have created a user-defined type by the name of tree node. I will need a variable to point towards the first node, and that will be of type integer. That will be known as my root pointer, type integer. I will need a variable to tell me which available node is, which node is available for me for adding new data. That will be my free pointer, again of type integer. I need to declare an array. My array is called tree, is size 7. It has 7 nodes on it. And the type of array is of tree nodes. So basically what I have is I have 7 nodes. I have an array of 7 tree nodes. At each index position, I have basically reserved space to hold these 3 values. Okay, now let's look at the procedure for initializing an empty tree. There's no values here. There are no data here. I just want to reach this stage first, an empty tree. So what happens is that I need a loop, first of all. Like we did for linked list, we're going to have a similar loop over here. I assign my root pointer as null pointer because there are no nodes currently added to my binary tree. So my root pointer will have null in it. The next available node I have is the first node actually. So my free pointer is assigned with one. The first node, the data that you try to add will be added in the first node right away. And now let's initialize my rest of my nodes. So I have my array over here. I will access each node through this loop. So basically I'm accessing the first node, then the second node, then the sixth node based on the index values in this tree. And this loop will run six times. So I will be accessing all, only not all, but only six nodes. I have to give it special treatment for the seven nodes, and as we did for the linked list as well. So for the first six nodes, simply what I'm doing is that I'm simply accessing each node and assigning the next value, the value of the next node towards the left of the current node's left pointer. So as mentioned before, an empty linked list is connected via the left pointer. So first node is pointing towards the second on the left pointer. Second node is pointing towards the third on the left pointer, so on and so forth. So similarly, that's what we're doing over here. We're accessing each node and simply assigning the next pointer's value on the left side. So if I'm at index position 1, I'm at the first node, my left pointer will have index plus 1, that is 2 on the left side. If I'm the next time this loop runs, I will be accessing the second node and the left pointer will have 1, 2 plus 1, 3 in it, so on and so forth. The final iteration for this loop will have the sixth node, and on the left, I'll be connected with the seventh node on the left side, and I will exit the loop. On the seventh node, so since seventh node is my last node, it should have both left and right. Okay, for the time being, just forget the right, but it's not connected towards anything on the left anymore because there are no more nodes after the seventh node. So that's why I simply access the seventh node in my array tree, and in the left pointer field assign the null pointer value to it. That's it. Now you must have noticed that in this loop, I'm not doing anything with the right pointer. Now there are two ways of doing this. One way is that you can assign null, because it should be null to it, because there's nothing here. It should have nothing here. So one thing you can do here is that in this loop right here, add one more line over here in which simply what you're doing is that tree index dot right pointer assigned with null. So basically, if I add a line over here, it will look something like this. Tree index dot right pointer assigned with null pointer. We can do this right here. So in this loop right here, in this loop, we're taking care of the right pointer as well. So what happens is that when this procedure is completed, my left wise, I'm connected towards, if I'm at the nth position, I'm connected towards the n plus first position. First connected to second, second connected to third, sixth connected to seventh, and the final seventh node is connected to null. Whereas on the right pointer side, since my empty binary tree is connected towards the left, the right has nothing to do with it. Right is all null. So simply at each node, I'm assigning the null pointer at the right. So we can do this right here, or there's another option which is being used in this algorithm. And that option is that simply do this procedure when you're adding a new node to your binary tree. Now imagine this, I'm adding a new node to my binary tree. As you know, just forget everything, just focus here. I have the right pointer over here and I'm assigning, this is my new node. I'm assigning a null at this point on the right pointer. So you can do this later on, or you can do this right here as we did it in the loop. That's your choice. So if you do it here, you don't need, that's redundant to add that line over here. If you want to do it there, that's also fine. So in either case, our goal is to make sure that initially the right and left pointer, because the node is yet not added in my binary tree, I just added new value to my node. That means my new value is yet to be placed in my binary tree somewhere. So that means both left and right should have null in it. So that's the most important point. The left pointer, why it has null in it, I will explain. But right now, the right pointer can be added null to it right here, or it can be done later. That is completely up to you. So when this procedure ends, initialize tree procedure ends, I will have a binary tree that has values in this sequence. This is the status of an empty tree. Root pointer has null in it. Free pointer is pointing towards the first node available, and all empty nodes are connected leftwise. The seventh node has nothing connected to the left. And maybe you added a line here to point had right to have null in all the right pointers, in which case all of these will have null in it. Or you can do this later at the time when I'm actually adding a new node in my binary tree. That's up to you. So in either case, we have achieved this state after your initialized tree procedure, initialized tree procedure ends. Okay, so now let's move on to the next feature added, included in your binary tree, is what happens, what are the sequence of steps that take place when I am to add a new node with a new value in my existing binary tree. Now it's like it goes that again, there's a great chance that my binary tree is empty. So, or it's full, it's empty, it's full, or it's partially filled. These are three possibilities that I have before this code runs. The first thing I'm asking, the first question I'm to ask, the most vital of the question is that, is there room in my binary tree? Is there room in my array of nodes? Because if there is room, if there is any node free for me to use to add data to, only then will this entire algorithm run. And if there is no room, this algorithm will not run at all. So that's why in my insert node, I'm taking one character as a parameter. I'm taking one character, one letter, one string type value, A, B, C, D, whatever it is, as a parameter. And based on the contents of this value that is being passed as a parameter, I will decide, my algorithm will decide where this node is to be placed. Obviously, what you have to understand is that when a node is added to my binary tree, it is always a leaf node. It always a leaf node. So basically, if as you can see here, I added D to it, it always adds as a leaf node. Every new node that I add to this list will always be a leaf node. Is it on the right? Is it on the left? That's another story, but it will become a leaf node because it was the last added node. There's nothing added after it yet. So exactly that's what's happening over here. So I pass a string type value as a parameter, and based on the string type value, decision will be made whether that leaf node ends up on the left of an existing leaf node or on the right of an existing leaf node. Okay, now, by the way, I said existing leaf node. It's not necessarily the case, because let's just say that I want to add the letter T to this list. Now, S is not a leaf node because it has at least one node on the left to it. So T would most definitely end up on the right over here. So now a new node can be added to an existing leaf node, or it could be added to a node which has maybe one position free. In either case, decision will be made based on the value that's passed in this parameter. Okay. So the first question I ask, is my free pointer not equal to null pointer? Now, if this condition is true, only then will this code run. And what that means is that there is space in my linked list. If this condition is false and my free pointer is in fact equal to null, like it was over here, that means my seven index position array, or an array of 7 nodes, all nodes are used, and I know I can no longer add any new nodes, and my code will not run at all. But since if this condition is true, I can proceed here. Now, who will tell me what is the next available node for me, available to me to use? Obviously the free pointer. I will refer to the free pointer like we did in linked list. The same principle applies here. I will look to the free pointer. Okay, tell me which is the next available node. The free pointer, whatever it was, will become my new node. So this line is simply assigning that next available node as my new node pointer. So if my free pointer was saying that index position 6 is now available for use, my new node will be index position 6. Okay. Next task is I need to update my free pointer to point towards the next available free node. Obviously, all free nodes are connected via the left pointer. That means I will go to my existing free pointer. I will access the left field. So if, for example, current node that I've been used is node number 6, my next available node will be node number 7, because as you can see here, my table says, my empty table says, after 6 comes node number 7. So basically, I'm updating my free pointer as we did before, because without doing this, my next available node, if I use it, will come back to 6 and I will override existing data, which is wrong, because I have to update my node. I have to update it. And the way to update it is that my current free node, the left pointer of my current node that I just assigned as my new node, will tell me which is the next available node, the left pointer only. So what we do is we access the left pointer of my currently used current free pointer, and I will call that as the next free pointer. So if I was at the 6th position, the 7 is placed on the left field. Now my next available node will be 7. And same as 7th, next time this code runs and 7th node was the last node, I will use my 7th node as my new node. And what comes here after the 7? What's on the left of 7? That's null. And the next time this code will no longer run because free pointer has null in it, and I will exit. This is how it's automatically being updated as we go, as a linked list is, the binary tree is automatically being updated as I'm adding values to it. So all we did over here is that I referred to the free pointer for the next available node. The free pointer told me that this is my next available node. I called that my new node, and my next free node will be pointed towards the current free pointer's left pointer. So that's what we're doing over here. So I look to the left pointer of my current free pointer, and that will become my next free pointer. And this is all we did so far. We just simply assigned a new node and we updated my free pointer so far. Okay, now these three lines refer to my new node. Right now, just imagine that this node is floating in the air somewhere. It has no position. It has not been attached in the tree yet, but is floating in the air, is suspended in the air. And we are yet to decide where it's to be attached. Now it's in the air somewhere. Meanwhile, what we do first in this available node is right away, we access the data field of this new node that we just used and give it the new item that we passed as a parameter. So the value is stored in the data field. And since it's not connected towards anything yet, and most probably, yes, as mentioned before, this new node will be added as a leaf node. That means its left and right pointers should both have null in it. So what we did is we took this node, this suspended in the air, not connected to anything node, and simply added the new item that I passed as a parameter to the data field. And since it will become a leaf node in my grander binary tree, I add null to both left and right. So once this is done and I have a suspended node in the air, now I will decide where it should get attached in my overall binary tree. So this whole sequence of events that takes place for making a decision of where this newly added node must go. Now, as we did with the linked list, we have to find a place to start. The linked list uses the start pointer to guide the algorithm from the start, and the start node then points towards the next node, so on and so forth. The same concept is applied here, but the value, the variable, the identifier changes. This time we're looking at the root pointer because the root pointer is the first available node. Now, I will start searching for a place for my newly added node by first looking at the root pointer. Now, there's a great chance that there are no nodes in my binary tree right now, and that would mean that root pointer has null in it. Does my root pointer have null in it? If yes, then simply do what? Call your new node pointer, the new node. For example, your node number 1 is your new node because it's the first available node and you have no nodes currently being used. So your new node will instantly become the root node. And every other node that's after from this added from this point will be in reference to the value in my root pointer. But this is only if my root pointer is equal to null, which means my binary tree is currently empty. But if this is not the case, that means my binary tree is partially filled and I will have to search through the nodes to eventually find a place where this new node is to be attached. Now, how do we do that? This process is known as finding an insertion point. What's happening here is that obviously, again, we need a place to start. What better place to start than the root pointer itself? Each node that I'm evaluating right now and finding whether or not this node is appropriate, I should move towards the left of this node or towards the right of this node, it would be called as this node pointer. So for example, I want to add D to this node, to this binary tree. I will look at the root node. I will start from the root node. And currently I'm evaluating the contents of this node, comparing my D to this node. If I move towards the left of this node, I will move towards the left. If I need to move to the right from this node, I will move to the right. And at each subsequent stage, if I have moved, for example, towards the left, now I will be evaluating this node and comparing it to the value that I just want to add. And based on that, I will decide either move towards the right of this node or towards the left. If I move towards the right, then I will be comparing the value of this node with my value that I just added, and I will decide whether to move towards the left or the right. So what I'm trying to say here is, what it means is that at each stage that the node that I'm looking at and deciding that should I move towards the left or towards the right? That is this node right here. And that's aptly called this node in the algorithm as well. So the node that I'm looking at right now and deciding to move from left or right from the current position is referred to as this node in the algorithm. So what I do is that I will start at my root pointer. The root pointer tells me which is my first node. And this will also be the node that I'll be accessing and comparing the contents of with my new value. So I will call my root pointer this node pointer. So each node that I am evaluating and deciding whether to move to the right or left will be known as this node pointer. And since I'm just starting this process, I will look at the root pointer first. So my root pointer, my root node is my first this node. Okay. Now, this is a loop right here. What does the loop say? As long as this node pointer is not equal to null, what we do is simply, if I have to move, that means if it's not null, I have to move either left or right because it's actually used. If this node becomes null, that means I have found a place that I can add value somewhere. So just look at this. Is my this node pointer null? No, it's not. It's used. I move to the left. Is this node pointer null? No, it's not. Move to the right or left, either way. Is it null? No, it's not. Is it null? No, it's not. I had to move towards the left because of the contents of what I'm trying to add. Is it null? Yes, it is. So that means I stop here. I stop here, either it was towards the right or the left. Same thing applies with any position. I'm adding the letter T. Is this node null? No, move to the right. Is it null? No, move to the right. Is this node null? Yes, stop here. This is the place where we'll be adding a new node. This is how I decided. So as long as this node is not null, I will keep on either moving towards the left or the right, okay? But since I am moving from this current position, and I may have to add my node, the newly added node, either towards the left or the right of this current position, I have to keep a record of the place I just left. As you remember, in the linked list, we had kept record of previous node in that too, because the new node that I'm adding is with reference to the previous node that I just left. Exact same thing is happening here. Since I'm going to be moving out of this position, I have to keep record of the previous position as well. So that's why before moving, I keep record of my previous node. So what I do is I assign this current node that I have this at this current position I am. This will become my previous position because now I'm moving. Where am I moving? That depends on this thing right over here, this decision over here. So since I've decided to move, I will assign the current node that I'm at as my previous node because I will move. It will become my previous node. Now, am I moving towards the left or am I moving towards the right? That is to be decided based on this if condition. How is this decision made? If at the current this node, the data is greater than the item I'm trying to add, right here. If at the node right now, the data is greater than my new item, that means the new item should come at the left of this current position. So I am trying to add D. I start searching at this node, D. So is D lesser than this node data? Yes, it is. So that means I have to move to the left. If it is false, the decision I just asked, if it's lesser, if it's false, that means the new item is greater than this. That means I will move to the right. So that's basically what I'm asking here. Is the current position, the data at the current position I am looking at right now, greater than the data I'm just trying to add? In which case, this to be added data should belong towards the left of this current data. So how do I decide whether or not to move to the left? Simply ask this condition, ask this question. If this question is true, I have a flag over here. This flag will become true if I have to turn left, and it will become false if I have to turn right. You see this flag, it says turn left true, turn left false in case of moving towards the right. So if this condition is true, that means the position I'm at right now, it has a value that is greater than the value I'm trying to add. That means this newly added value should add to the left, in which case my turn left flag will activate, it will become true. And what will be my next this node? Obviously the left pointer will be used. So the next available this node will be what node? It will be pointed by the left pointer of the current this node. So the next this node will be the left pointer of the current this node if I move to the left. However, if this condition was false, that means the newly added item that I'm trying to add to this binary tree is greater, it's not lesser, it's greater than the data I'm at right now. In which case, this newly added item should appear at the right. In which case, this condition will become false and I will come at the else. In which case, turn left will become false. And the next this node that I'll be referring to will be accessed through the right pointer of the current this node. In which case, the next this node is at the right of the current this node. Now, a special caution here. If you remember, before taking a decision towards the left or the right, I've saved the state of the previous node here. So if, let's just say, after either moving towards the left or moving towards the right, either way, if either moving towards the left or the right, I have taken the decision to move towards the left or right, and that left or right pointer is null. That means I have reached the end of my binary tree. This condition, this while loop will become false and I will exit the loop. And when I exit the loop, I'm left at this stage over here, either here, say, let's just say I exited, this was my previous node, and my current this node is either this one or the right of this one. They're both null, by the way. But that flag, remember, turned left, that will tell me that my previous node is this one, and the newly added node should either come on the left, because turn left was true. I will add the newly added node on the left. And if the turn left was false, that means I exited based on null, and the newly added node will come on the right of my previous node. So that's what's happening over here. So I will keep on doing this. I'll move towards I will follow my binary tree from the left, right, left, right? Depending on this condition. But as soon as I enter my last node, if I'm at my leaf node, my comparison will take place as it's doing over here. And I will obviously move from either left or right from this current leaf node. And when I do decide moving on the left or right, first of all, I will assign my current leaf node as my previous node. And this decision will tell me that am I accessing, well, am I accessing the right side of this current leaf node for adding this new node, or the right side or the left side, based on this condition. So if this condition becomes true, that means that my newly data item that I'm trying to add on my leaf node should end up on the left side, So in this case, when this condition became true, my turn left became true. And this node will obviously be null, because previously this node was a leaf node, and there are left, right, both null here. In which case, what I will do is I will access the left pointer of this current leaf node, which will, of course, what will be null, because this node's left pointer is null. Now this node will have null in it. And when I come back up here for the next time around, next iteration, this comparison will no longer be true, and I will exit the loop. And I exited the loop right here somewhere. Now the flag will tell me, did I turn left? Yes, you did. So that means since I exited my loop, I have reached a position which I should be adding the new node to. And since the flag says turn left true, that means I will add my newly added node on the left of this existing leaf node. If it was false, I will add it to the right. But the thing is, how did I reach here? How did I reach a leaf node? Obviously, till this pointer becomes null, I will keep on either moving towards the left, right, until either I reach a leaf node and there's nothing on the left or the right. And this node pointer, since it's null, I will exit the loop and I will look at the flag, and if the flag will tell me add it to the left or the right one. That's what's happening over here. So now, since I exited the loop, and by the way, my leaf node that I'm talking about has already become a previous node, because this was the last time this loop ran. And the next time around, this node pointer had null in it, and I have a record of my previous node. My leaf node is my previous node, right? I check, did I turn left before exiting the loop? Yes, you did. In which case, what I do is I will access my previous node pointer position and simply access the left field of that previous pointer and give it the value of my newly added pointer that I want, new node pointer. However, did I turn left? False. In which case, I will access this is my else state. I will access my previous node pointer. I will go to the right position and add this new node pointer on the right. Simple as that. So adding the feature of finding a node in my binary tree requires us to first decide on or take an input from the user of what value they're trying to find. That value will be passed as a parameter to this function over here. Okay. Keep in mind that this is a function. This was a procedure. This is a function. That means it will be returning something upon finding or not finding something, whatever it is. Similar concept was implied for linked list as well. We were applying the same thing, that we're taking as a parameter some value, and based on that value, we're searching our linked list node through node until we either find it, we will return the index position of that node, or we don't find it, in which we return null. Same concept is being applied here, but searching through nodes varies from the linked list. So obviously, as always, when I'm trying to search something in my binary tree, the best place to start from is the root pointer. Okay. The node that I'll be looking at right now and investigating whether or not the contents of this node are the value I'm looking for is aptly called this node. So since I'm starting at the very top, My root pointer is my this node pointer. I will access this node pointer and will see the value of this node pointer, compare it to what I'm looking for. If it's found, return it, finish. If it's not found, I will ask, okay, is the value that I'm looking for lesser than this node pointer's value or greater? And based on that decision, I will either move towards the left or the right and either find the value or not. Okay. So in any case, I will start at my root pointer. It's the first this node that I'll be looking at. We have a loop here. Until this node pointer is not equal to null, this loop and the data in this node pointer is not equal to the item I'm looking for, my loop will keep on going. So this is a complex condition here. Both have to be true. Either I've not reached the end of this node of my binary tree, or I have not found the data. I will keep on going. If I exit this loop, it will be because of one of these conditions has become false. That means either I have reached the end of my node or I have found my value. If I exit this loop because of reaching the end, that means I reached the end without finding it. In that case, I will be returning null, did not find it. If I exit this loop because of this condition becoming false, that means I found the value and I will simply return the position I'm currently at. Found it at this position, simple. In either case, this is how this condition is being used. So what's happening inside my loop? I'm asking this condition. I'm at this point right now. Is the data at this point, as this node point, is the data greater than my searched item? Is it greater than my searched item? If it's greater, then obviously my search item that I'm looking for belongs on the left somewhere. In which case, I have to follow towards the left position. How do I follow towards the left position? Okay, now one thing to note here is I'm not making any changes. There is no changes. I'm not deleting or adding nodes here. So there's no need for keeping record of previous. Simply move on to the left. There is no need from previous node pointer here. Simply move. So in this case, if this condition is true, that means my value, the current node's value is greater than the item I'm looking for. So that means the item that I'm looking for belongs at the left of my current position. So that means I have to follow to the left. So that means this pointer will be actually the left of this pointer. So that's what I'm doing. I'm updating the current this pointer. How? I will access the tree at this position. I will access the left field of this current node, and that will become my next this node. And then I will go back up again, make this comparison again. Either it's null, I will exit the loop, or either the data is there at the current this node. In any case, if none of these conditions have changed and this loop whole condition is true, I'll come back here. I will ask again, is the current this node data greater than my search item? Let's just say that now it's not, this condition is false, which means that my search item that I'm looking for is not lesser than my data at the current position. It could be equal or it could be greater. Okay. If it's greater, then my data that I'm looking for, that means my search item is at the right. The item I'm looking for is at the right. If this condition was true, that means that my search item is at the left. If this condition is false, that means my search item is on the right, in which case I move towards the right. So I move towards the right. How do I move towards the right? This else condition will run, and my next this node pointer will be calculated with respect to the right pointer of my current this node pointer. So I will access my tree at this position, access the right pointer field of this node, and that will become my next this node. So either I will find the node or not. In any case, when I exit the loop, I will simply return this node pointer, the value stored in this. So if the value I returned was null, why null? Because I exited the loop because of this condition becoming false. If I exited the loop because of this condition becoming false, that means I traversed the whole tree and I did not find what you were looking for. In which case, returning this node pointer will result in null being returned. And if null is being returned, it can be understood from here, from this outcome, that the value that you were looking for was not found in this tree. However, if I exit the loop based on this condition becoming false, that means this node pointer is actually not a null value, but it's an index position hold of the node holding the value that I'm looking for. And I'm simply returning that index position, telling you that that value that I'm looking for, this value is located at this node pointer. So either this function is returning a non-null value, telling you the position where the value is that you're looking for, or it is returning a null value, telling you that the value that you're looking for is not present in this binary tree.